Welcome everyone to my presentation on the 1996 Nobel Prize in Chemistry for the discovery of fullerenes, which is a kind of carbon molecule. So first I'm going to tell you on how they got to the Nobel Prize, so the road to Sweden, which includes the time before their experiment, so before 1985, then the discovery, further experiments they did after the discovery, and then finally the Nobel Prize. I'm also going to tell you about applications of fullerenes in solar cells, which is just one application of fullerenes. These are called organic solar cells, and the electron affinity of the fullerene is important for this. And I'm also going to tell you about the current state. So let's meet the laureates. We have Robert F. Curl Jr., who is also known as Bob Curl, who was born on 23rd of August 1933 in Texas. And he got interested in chemistry as a little kid when he got a chemistry set. He studied chemistry at Rice Institute, which is now known as Rice University in Houston, Texas, and did a PhD in chemistry at UC Berkeley. He did a postdoc at Harvard on microwave spectroscopy, and then went back to Rice as an assistant professor. Then we have Sir Harold Kroto. He is also known as Harry Kroto. He was born on 7th of October 1939 to Jewish refugee parents in the UK. He was interested in chemistry, physics and maths at school and decided to study chemistry at the University of Sheffield. There he learned that you could also study architecture, and he thought that had he known earlier about this, he might have done it because he's also interested in art, and architecture combines his interest in art, science and technology. He then did a PhD in molecular spectroscopy at the University of Sheffield and did a postdoc in Canada and in the US, both working on spectroscopy. He was then offered a permanent position at the University of Sussex in the UK. He died on 30th April 2016. Then we have Richard E. Smalley, who's known as Rick Smalley. He was born on 6th of June 1943 in Ohio. He got interested in science because his mother did a Bachelor of Arts while he was a teenager, and she was fascinated by the Foundations of Physical Science course and would tell him about it. He studied chemistry at the University of Michigan and did a PhD in solid-state spectroscopy at Princeton University. And after a postdoc, he went to Rice University and became an assistant professor, where he collaborated with Bob Curl and where he developed a supersonic laser beam spectroscopy, which was also used by collaborators in the industry, namely at Exxon. So let's go to 1967, where Rick Smalley and Harry Kroto both went to the Montreal EXPO. They didn't know each other at the time. At the Montreal EXPO, there are countries that exhibit themselves in pavilions. Now, the interesting pavilion for us is the US Pavilion, which is a geodesic dome that you can see here. A geodesic dome is a sphere, or an approximation of a sphere, by interconnected straight lines. This dome was built by Buckminster Fuller. Now, let's talk about what was known about carbon at the time, so in the early 1980s. It was known that carbon formed a diamond structure, which is a face-centered cubic. And you can see it here. So one carbon is attached to 4 other carbon atoms. And this kind of attachment is called sp3 hybridization, and I'm going to explain this to you now. So electrons are described by their quantum numbers, which describe the wave function that they can have when they're around an atom. And this is also called an orbital. Now, the shape of the wave function or of the orbitals is determined by the quantum number. We have the principal quantum number n, which comes from the quantization of the orbital angular momentum in the Bohr model. We then have the orbital angular momentum quantum number L. and we have the magnetic quantum number m, which describes the direction of the angular momentum vector, basically, or the orientation of the orbital relative to some direction, usually the z-axis. So this is a 1s orbital, this is a 2s orbital, this is a 2p orbital, or these three are 2p orbitals, and each orbital can have 2 electrons in them because of the Pauli exclusion principle, which says that fermions have to be different in at least one quantum number, and so they can be different in their spin quantum number, and 2 electrons can populate one orbital. Now, how do we make covalent bonds with these orbitals? So in a covalent bond, one electron is shared between, or 2 electrons are shared, 2 electrons are shared between 2 atoms. And so here we have carbon, which has a 1s orbital filled with 2 electrons, which is not shown here, a 2s orbital filled with 2 electrons, and 2 p orbitals filled with 1 electron each, which are the 6 electrons in carbon. But in diamond, they make 4 covalent bonds. So how do we get 4 covalent bonds out of this? And this is explained by orbital hybridization, where the s and the p orbitals combine to form, in this case, 4 sp3 orbitals. And these sp3 orbitals can then form the shape that we've seen before. So let's go to graphite. Graphite comes in hexagonal unit cells. And here the carbon is planar, not like in diamond. And this carbon is sp2 hybridized. So in this carbon, we take 2 p orbitals to make, together with the s orbital, 3 sp2 orbitals with 1 electron each, and 1 p orbital which contains 1 electron. And now these p orbitals can align in such a way that the electrons can share them that are in the p orbitals, and this is called a pi bond, or this is what makes the double bond in double bonding structures. And the electrons in these pi orbitals can delocalize over this sheet here, and this is what gives the electronic conductivity along the sheet in graphite. Now let's look at the year before the experiment, which is 1984 to 1985. Kroto was interested in the radioastronomical detection of molecules in interstellar space. Specifically, they had found polyanes in interstellar space by their microwave spectrum. Polyanes are carbon triple bond, carbon single bond chains that alternate between triple and single bonds. What they didn't know was how these polyanes would form in space. So they wanted to find a way to test how they could form. And for this, he set up a collaboration with Smalley, because he had an apparatus that would allow him to simulate the outer atmosphere of a carbon-rich red giant, because they thought maybe these polyanes formed there. In the same time period, Rolfing, Cox, and Kaldor at Exxon Company, which is an oil company, did research on graphite using the supersonic beam laser spectroscopy apparatus of Smalley. They actually used a clone, not Smalley's, but it was the same one, and they investigated carbon clusters. And now they found in their experiment carbon clusters from the size of 1 carbon to 30 carbon, which occurred in both even and odd numbers. And then from 40 carbon onward, they observed something strange, namely they only saw even numbered carbons. You can see their results here. So up to about 30 carbons, you have both even and odd numbered clusters, and these clusters are polyanes. And here you only have even numbered clusters, and they thought that maybe these were also very long polyanes chains that would stack together in some hexagonal array that is called carbene. Now, at the beginning of September 1985, Kroto arrived at Rice to do his experiments simulating the atmosphere of red giants. So here is the experimental setup. In the experimental setup, you have high density pulse flow of helium that goes through here. It passes over a graphite disc. This graphite disc is hit by a laser, and that laser evaporates the graphite into the helium stream, and in the helium stream, the carbon atoms are cooled down and start to form clusters due to collisions with helium, and then they are supersonically expanded, which leads to further cooling, which can lead to larger clusters. These clusters then travel into a time-of-flight mass spectrometer where they are ionized by another laser. And then the clusters are electrostatically accelerated. And depending on the time they take to take the ion detector, you can figure out the mass of your cluster. And here is what they found. They also found only even number clusters from 40C upward, as had Rolfing and the other people at Exxon. But they also noticed that there was something strange about the 60C cluster, because that one appeared to be prominent compared to the others. And so they used different conditions to try and maximize the signal for the 60C cluster, so to maximize the amount of 60C that is produced in their apparatus. And so here at the bottom, they used 10 torr of helium. Here they increased the pressure of helium to 760 torr, which caused better clustering conditions. And here they changed the conditions in the integration cup to improve the clustering conditions even further. And so they found a very prominent signal for 60C and a secondary signal for 70C clusters. And now the big question was, what is so special about the number 60? So the first idea that they had was that maybe there was a flat sandwich solution where hexagonal sheets, part of hexagonal sheets were torn out of the graphite and kind of stacked together. But the problem there was that they had electrons that weren't bound to atoms in the way they should. So they had dangling bonds, and they couldn't figure out how that mechanism would prefer 60C clusters. So they had another idea, which they called the closed solution, in which the hexagonal sheet would somehow curl to form a closed structure, and that structure might look like a geodesic dome. So they decided to look up Fuller's work, but then they got distracted by other things and didn't work on the structure any further until 2 days before Kroto's departure. They decided to try to solve the structure again, and Smalley started working on a paper model using hexagonal paper cutouts that he tried to stick together to form a closed structure. But he couldn't get it to work, and it was approaching midnight, and then he remembered that Kroto had said that he had built a geodesic dome with his kit, and that he thought to remember that it might include pentagons in this geodesic dome. So Smalley cut out pentagons because carbon does readily form 5-membered rings, pentagons, so that's okay. And he stuck 5 hexagons to the pentagons, and it curved into a bolt shape, which is very exciting. So he kept on working, and then with 12 pentagons and 20 hexagons, he actually managed to form a structure that had 60 vertices, so 60 carbon atoms that was closed. And so they had found the solution of how to find a closed 60 carbon structure. Now, Curl wasn't completely convinced, because he wanted to know whether the pi bond system works out. So whether you have a system of pi bonds that allows the electrons to be completely delocalized over the entire sphere. This is called an aromatic structure by the chemists. And so they took paper labels with double bonds drawn on them and stuck them on the sphere, on the paper sphere, to figure out if such a system of double bonds and single bonds alternating would work. And they actually found that it does work, that you can have alternating double and single bonds. So the structure is aromatic, so they all thought that this must be the solution of why the C60 signal is so prominent. Now, they didn't know what this structure was called, so they asked the mathematicians in their department, and they got back to them and said, well, basically, you have made a football. The football is also called a truncated icosahedron, but they included the picture of the football in their 1985 Nature paper, which got them the Nobel Prize later on. And they named their C60 structure Buckminster Fullerene after Buckminster Fuller, the architect. Because it's quite a long name, it's usually also called buckyballs. And what is really cool about the structure, that each carbon atom on this structure is exactly the same. So it experiences exactly the same environment. Now to some other important experiments that were made after the 1985 discovery. In the years after, they did experiments to try and figure out whether their proposed structure was correct, and these were infrared and UV absorption experiments, for example, but one of the most important experiments was by Kretschmer and colleagues, and they figured out a way to produce 100 milligram of buckyballs per day, which was a lot more than the other methods they had used so far. So here you can see the apparatus that they used to produce 100 milligrams of buckyballs per day. You have a graphite rod which has a current flowing through it that vaporizes the graphite rod, and that carbon vapor condenses here to form soot, which also contains C60. This soot is then scraped off of the condensing unit and dissolved in benzene, which looks like this. Benzene also has these pi bonds, so delocalized electrons over the whole ring. And in benzene, C60 dissolves, whereas the other soot particles don't, so you can filter it off, and then you can dry your benzene to get solid C60 crystals, and they call these solid C60 crystals fullerite. So now that we have a way of making a lot more of C60, they could do the carbon-13 NMR on it. So for nuclear magnetic resonance, I suggest you watch Yuval's talk first, where he explains nuclear magnetic resonance in much more detail than I do here. I am just going to give you a very short and simplified way of looking at it. So 13C has a nuclear spin of 1/2, but it only makes up 1.11% of all natural carbon. Now that nuclear spin, because it's kind of a spinning charge, it results in a magnetic moment. And in the absence of an external field, these magnetic moments are randomly orientated. Now if you apply an external field, B0, the spins will align because of the magnetic moment, and the energy required to flip a spin, delta E, is given by the quantum number m, which is 1/2, or plus minus 1/2 actually, for the spin up and spin down alignment, and the gyromagnetic moment, or ratio, which depends on the nucleus you have, and you have the external field that is applied. Now for carbon, usually you need a radio frequency field of 50 megahertz to flip the spins. Now, how much, what frequency is actually required to flip the spins depends on the environment that the nucleus is in. So it depends on the electrons around the nucleus, because electrons are moving charges, and so they tend to generate a field, and that field can be either parallel or anti-parallel to the external field. And so the nucleus either sees a higher or a lower magnetic field than the externally applied field. And so the frequency that is needed to change the spins changes. Here is what such an NMR instrument looks like. You have your sample in here. This here is the magnet. Because you need a high magnetic field, you use superconductors, which are cooled. So here is the spectrum for C60. The C60 is just a single line, because all of the carbons have exactly the same environment. All of the carbons are exactly the same on this view. This line here is from the benzene solvent that they used. Now, to compare this to a structure where not all carbons have the exact same environment, I'm going to show you the spectrum of C70, which has 5 peaks labeled A to E here. And here is a depiction of the different environments of the carbons. So with C70, you have a row of hexagons added in the middle, and that bulks it out a little bit. And the carbons here in the middle, they have different angles of their bonds than the carbons to the side, and these different angles cause slightly different electronic environment. And then here you have these carbons, which see the carbons in the middle and sort of the half sphere here on the side, and so they also have a slightly different environment, and so on to the outer carbons. They all have a slightly different environment that's labeled here, corresponding to the peaks you see in the figure. Now, in 1996, they got the Nobel Prize for their discovery. And here you can see the articles published on the topic of fullerene from the year 1985, where you have the first article published, up until 2019. It is important to note the importance of the 1990 improvement in the method of making C60. Because from here we had the first paper, then we had some more papers, then in 1990 we had the new method, and then after that we had like 300 papers published on fullerene. So this really shows it. Now let's go to an application. The application of fullerene in solar cells. So if you have an organic solar cell, you want to produce a charge separation by transferring an electron from a donor to an acceptor. And this is done as described here and as also shown here. So you excite the electron in the highest occupied molecular orbital to the lowest unoccupied molecular orbital by absorption of a photon in the donor. Now, the distance between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, or HOMO and LUMO, as they're also known as, is kind of like the band gap in semiconductors. And then through a process of complex formation, this electron is transferred to the LUMO of the acceptor. So now for this process to work well, you need an acceptor that likes to accept electrons. And so the electron affinity should be high. Now let's look at how fullerenes are a good electron acceptor or have a high electron affinity by looking at the UV photoelectron spectroscopy experiment. In this experiment, they produced C60 using this supersonic beam laser apparatus or a similar version that was used in the original experiment that won the Nobel Prize. The authors introduced naphthalene to the carrier gas, which they ionized with a laser to to get free electrons, and these free electrons would then attach to the C60 clusters as they were formed, generating C60 anions. These C60 anions were mass selected by sort of a time-of-flight mass spectrometer, and then the electrons on the mass selected C60s were detected using another laser, in this case a 6.4 electron volt laser. You can see the result here. So it took about 2.6 to 2.8 electron volts to detach that first electron, which is the electron in the LUMO. And then you see a gap, and then you see at somewhere like 4.5 electron volts another peak. And this gap of 1.9 electron volts is the gap between the HOMO and the LUMO. So the current state of solar cells, where you have fullerenes as acceptors because they have a fairly high electron affinity and a decent band gap. You need to also make sure that the interface between the acceptor and the donor is maximized because they need to be in physical contact to actually transfer the electron. This is done with bulk heterojunction solar cells that are shown here with the donor and the acceptor mixed together kind of randomly. There is still improvement needed in the fullerene acceptors. They are trying to get a higher LUMO for the fullerenes by adding other molecules to it. And currently polymer fullerene solar cells have an efficiency of 11.7%. So this was all that I wanted to tell you. I think it is a super fascinating topic, and there are many, many more parts to fullerene research that I don't have the time to go into. Here are the some of the references that I used. I can especially recommend these two books and this paper here, which is written quite conversationally, and I'll also leave some further interesting links in the description box to YouTube videos and to an instruction on how to make your own paper fullerene. So thank you for your attention.